Okay, welcome all to the Horowitz, the online Horowitz seminar meeting. Today we'll have Renan Gross from the Weizmann Institute to tell us about concentration on the Boolean hypercube via pathwise stochastic analysis. Let me also add that this time we've put the slides of the Horowitz seminar in advance on the Horowitz seminar website so that you can leaf back or forward if you lose Renan and want to see another definition again. Renan, thank you for coming, and please, you have the microphone.
Sure. Okay, I'll give the standard preamble. Thank you for having me in my own home. Of course, you have to say this, my own lecturer's home. To all you people with webcams turned on, thank you. This is actually my first Zoom talk, so I'll be happy to see some faces. And in any case, regarding what Asaf said earlier, he wants a nice talk. So if it's a nice talk, then later you go on, you can go to your friends and family and say, hey, I heard a nice talk despite the Zoom. And if it's a horrible talk, then we can always just blame the Zoom. So I'm actually on fairly comfortable grounds over here. Okay, it's a good thing they put the title on the first slide. So today I'm going to talk, I sometimes talk quite quickly, so please stop me and you can put questions in the chat. And even better, you can unmute yourself momentarily and ask questions. I have no idea, what you're getting from this, what you're not getting from this. So if there's some interaction, it would be really nice if there were some interaction. Okay, so this is an analysis seminar, and I deal with the analysis of Boolean functions. So today we're going to talk about concentration inequalities on the Boolean hypercube via pathway stochastic analysis, that is using some sort of stochastic process, which Ronen, who is here, and I developed, which help you look at all these inequalities. So are there any questions so far? Okay, no, everybody's all right. So of course, the usual warning, okay, we're going to see graphs here. I don't know, maybe you're not used to seeing graphs in real life, so your discretion is advised. Okay, so this is a short overview of what to do. We'll start with talking about basic concepts on the Boolean hypercube, variance, distributions and influences, stuff like this. It totally did not take me like 5 hours to draw this picture. Then we'll talk about functional inequalities and what sort of functional inequalities you can have specifically for the Boolean hypercube. Maybe some of you already recognize some of these guys. This is just a sneak peek, so don't worry too much about it. And then we'll see how we can use stochastic processes, in this case, Brownian motion, but eventually something which can give a much cooler, discrete, multi-dimensional process to show these kind of inequalities. Okay, so these are just some pretty pictures to get you interested, and something you can look back to in case you fall asleep or you lose me during the talk. Okay, so far? Yes, great. Okay, so who are our main players today? Our first main player is the Boolean hypercube, which we denote by -1 to the n. And it looks like this guy over here. This is can you see my pointer? This is a 4-dimensional hypercube. Here on the outside, you have one copy of the 3-dimensional hypercube, and on the inside, you have another copy of the 3-dimensional hypercube. So altogether, it's a 4-dimensional hypercube right here on your own screen. All right. And our main player on this cube is the Boolean function. So what is a Boolean function for me? It's some function with domain -1 to the n and range either -1 or 1. So it always gets true or false. And you can also think about it as 0, 1 if you like. And for us during this talk, white vertices on the Boolean on this cube will be 1. Okay, so here I have some function which some of the vertices are white, some of the vertices are black. So this is the function. Accompanied to these functions in this cube, we have the uniform measure, which we denote by mu. Okay, so if we just pick one vertex at random, or equivalently, if we pick every bit independently at random, we get the uniform measure. There is a 1/2 to the n chance to get every point. With this measure, we can take expectations. Okay, so for example, the expectation of f is just the average value of f when we pick x uniformly at random, which is just a sum over all points divided by 2 to the n. And of course, we have the variance. You can see it's an important main player because it's called in orange, so it's not black like all the rest. So the variance of a function is defined just like the variance of any random variable that you're used to in probability theory, just the expectation of the squared minus the square of the expectation. but we are dealing with a Boolean function. Boolean function's range is only -1, 1. So f squared is always 1. Okay, so another way we can write this is 1 minus the expectation of f squared. And we can open this up. And we can see, okay, I don't know, let's suppose that the expectation of f is smaller than 0. Okay, so let's say half the vertices, at least half the vertices are black. The expectation is smaller than 0. Then this number here will be between 1 and 2. So, and then you know, the main contribution will be 1 plus the size of the expectation. So basically the variance can be thought of as up to a constant of, I don't know, factor of maybe 2 as 1 minus the absolute value of the expectation, which in another term is basically the surface area. Okay, so it's basically just a measure of how large the surface area of, you know, the largest component you have in the function. Okay, so far? Yes. Good. Okay, Ron does like this, so I guess you know, Ron is a representative. Maybe Ron is a dictator. We'll see about this in a moment. Okay, so for the analyst about, okay, this is all right, an analysis seminar, not just a Boolean discrete seminar. So we have to do some analysis, right? We have to have some derivatives. So a discrete derivative is just defined as the difference between the value of some, you know, at point x. It's a difference between the value of the function when the ith bit is 1 and the value of the function when the ith bit is -1, and you divide by 2. So it's exactly what you would do when, you know, if you thought what a derivative had to be on the discrete hypercube. And then we can see that the derivative squared, it's basically an indicator function. Okay, it's 0 if the function does not change sign when you change the ith bit, but it's 1 if it does. And with this, we can define our second important player. You can see it's colored in blue. It's called the influence, or the ith influence of a function. It is defined as a probability that when you flip the ith bit, the function's value changes, hence influence. Okay, how influential the bit is determined by how many inputs, you know, this flipping this bit changes the value. And since this square of the derivative is just an indicator, then the influence is just an expectation of the square of the derivative. And the quantity which is usually talked about in Boolean analysis is the total influence, which is just the sum of all influences. Okay, and let's see an animation, which again totally did not take me like 7 hours to draw. So now I'm showing the cube and I'm showing some function. And if I look along this direction, okay, I know I call it the x direction, then I can see the influential bits, or the influential labels, edges. Okay, so here we have movement from black to white, from white to black, whereas in the internal cube, there's no movement at all. And if I count up all of the influences, so this is the total influence, and for every direction I look up at all the edges that cause me to change value, then I eventually get some sort of a surface area of f, right? If before we talked about the variance, it was the sort of like, you know, the volume of f, of the function f, then the total influence is sort of like a surface area, because it counts the number of edges going from black to white vertices. Okay, you know, you like isoperimetric inequalities. So let's see some examples of functions, some quick examples. We have Ron's the dictator, sorry. We have the dictator function, called so because it depends only on one bit. Algebraically, we just say that f of x equals, say, the first bit, and pictorially, it's here. You see that everything is pushed towards one side. All the black vertices are on the left side of the cube, on the white vertices on the right side of the cube. It's a balanced function, okay? It has the same amount of black and white vertices, so it has variance equal to 1. And the influence, well, it's always 0 if you move in a direction, you know, the non-dictate direction, and it's always 1 if you move in the important direction. So it's just 1 if x1, if I is equal to 1, and 0 otherwise. Okay. Our second totally different function is the parity function. This is a function which is just the product of all the indices, all the variables. Okay, so no matter how you change, whenever you flip a bit, you just change the value. And you can see this here in the cube, and you can see it in the equation. Again, half of the vertices are black and half are white, so the variance is 1. And the influence of every bit is 1, because no matter what input you have, you change, moving to flipping that bit, you always change the value. And on the opposite spectrum, in some sense, of the dictator is the majority function. Here you see the Knesset, which was in the news lately, I guess. I don't follow the news anymore since the corona. And with this function, you look at the sign of the sum of the input bits, or in other words, if the majority of bits is 1, you output 1. If the majority of bits is -1, you output -1. And for n odd, again, this is an equal number of black and white vertices. You get variance of 1. And if you manage to catch up during the talk, then you will see, when you have some spare times, then you can see that the influence is of order 1 over square root of n. So we see that we have all sorts of different functions with different properties. They all have variance 1. Okay, it's not really hard. Constant variance. They all have variance. Okay. So this really is like finding. Another one which will be important for us is called the tribes function, reminiscent of our ancient days when we used to live in tribes. We divide the input into small tribes, and I'll say what small is in a moment. And then the function's value is 1 only if there is an entire tribe whose value is all of whose members' values are 1. So here's my entire input. Okay, it's this long in string. I divide it into small tribes, which I call T1 to Tk. So this is the first tribe. This is the second tribe, and so on. And then for some input, okay, I get
Renan, sorry, there's some difficulty with the voice.
In this case, sorry.
Renan, there is some difficulty with the voice.
I'm sorry. So did I just like talk? And then...
No, I think it's the internet connection. Is it that other people also experience this difficulty? Yes. Yes. I don't know if there's anything you can do, Renan. Do you have other things open or something that you can?
Yeah, I'll just check if there's. I'll be back in a second.
Okay, sure.
Okay, I didn't do anything, but maybe something happened. Okay, you can hear me all right?
Okay, right. If you have a wired connection, that would
No, I'm afraid not.
Okay, very good.
We live in a wireless era.
Okay, please go on.
Okay, well, I say nonsense anyway. You can just fill in the blanks yourself, right? Okay. So do to repeat anything?
Renan, you were just cut for a minute. So I don't think you need to repeat the tribe function. Now you seem to be okay. So I don't know, there was some difficulty before, but if you have nothing to do about it, then please go on. And I certainly heard most of what you said on the tribes function. We see the slideshow very well. So you can continue.
Okay, okay. Good. Okay, so what I just finished up with this horrible, obnoxious function, that if we pick the right tribe size, then the influence of every bit is of size log n over n, and the variance tends to 1 as n goes to infinity. That's all I wanted to say, basically. So this is our fourth member of our, nice functions to consider whenever we think about what these inequalities say for different functions. Okay, and what sort of inequalities can we have for different functions? Okay, this is an analysis seminar, so we all know about Poincaré's inequality, but let me give a small reminder anyways. It's an inequality which is true for many sorts of function spaces, in particular this space, usually written in this form. So the variance of a function is smaller than some number c, okay, constant c, which depends on the space, times the integral of, the gradient, the size of the gradient squared of f, okay, d mu. And we have a mu, okay, and we have a gradient, right? We talked about the derivatives before. So we can apply everything here to the Boolean setting as well. And, okay, so as I said before, so the square of the derivatives, this expectation is just the influence of the ith bit. So the Boolean Poincaré is just given this form. The variance of f, which is a number between 0 and 1, is always smaller than the sum of all influences or the total influence, as it's called.
To a constant, Renan, in the end with a C?
Yeah, so this constant depends on the space, and here the constant is 1.
Okay.
You can also take it to be 2, I guess, right? But it's 1. In general, you know, I think this will appear later on the slide. So whenever the constant C appears, it can be any constant, even the same line. It's a self-magical constant, which is equal to itself, whatever. We don't care about constants really much in this talk. So, okay, good. So, so this is a Boolean Poincaré inequality, and for the dictator function, this inequality is is great because the variance is 1, and the influence of 1 bit is 1, and all the rest is 0. So we got 1 is smaller than 1, and it's actually tight. We here have a question: is this also the F1-Stein inequality? Actually, I don't know, but maybe someone in the audience knows about the F1-Stein inequality.
I think it's quite similar. There is something more general. When you have x1 to xn being independent random variables, then you can write a similar type of inequality for a function of them. So I think it is similar to F1-Stein.
Okay, I don't know what the F1-Stein inequality is, but I guess in 1 hour about I will look it up. So right now I can't comment. So we have tightness, going back to the presentation, we have tightness for this inequality for the dictator function, but pretty much for every other function, it's very far from being tight, and it doesn't really tell you anything much. This is because the variance is always a number between 0 and 1, but the influences, the total influence can be quite large, okay? For the parity function, for example, it can be on the order of n. And for many important functions, the sum of influences tends to infinity as n goes to infinity. So this really doesn't give you anything. And the question is, are there any stronger inequalities? Okay, like, you know, like in function spaces, we have all sorts of Sobolev inequalities and stuff like this. Are there any stronger inequalities for the Boolean functions on the Boolean hypercube? And the answer is, everyone's muted, but I hear yes, you know, yes. The most famous of these inequality called the KKL inequality, proven by Kahn, Calais, and Lineal in 1988. Okay, which says that the variance is not only smaller than the total influence, but it's actually smaller than the total influence divided by log of 1 over the maximum influence. Okay, this like sort of cryptic expression, but you can see that if the influence, you know, the maximum influence goes to 0 slowly enough or quickly enough, then even if the total influence goes to infinity, maybe this can somehow still remain bounded. So maybe we can actually have tightness in this inequality. It's better than Poincaré, right? The right-hand side is smaller now. Maybe we can actually have tightness for other functions apart from the dictator. So the answer is yes, and this is why we took so much time to learn about the tribes function. So for the tribes function, every influence of every bit is about of size log n over n, okay, up to some constant. And if I just plug it into the KKL inequality, on the left-hand side, I have the variance, which is 1. And on the right-hand side, I just put in, okay, every influence is the same. So the maximum influence is log n over n. So 1 over that is n over log n. And then I have the sum of n times log n over n. And if I do the calculation, it's just some constant eventually. And
Renan,
so the KKL inequality is tight.
Renan, we already know that for any Boolean function, the variance is at most 1. So what do you learn from knowing that it's at most a big constant C?
Well, the ratio between them is not going to infinity, I guess. So it's tight up to a constant. I guess being tight up to a constant is a lot better than being tight up to square root of n.
Okay.
Okay. Okay, well, we'll see about these kind of things later, but we'll see that sometimes you can learn a lot about the function if you know that it nearly saturates an inequality. So we actually have a result of this type, that if your inequality is tight up to a constant and not to a multiplicative constant, then you know something about this function. It has to tell you something about it. But good catch. Also, okay, good enough, that's good enough. So KKL, we say that it's tight for this inequality, for this function. But on the other hand, for the majority function, whose every influence is about size 1 over square root n, if you do the calculation, which we won't really do right now, you get that it's not tight, okay? Then this ratio goes, you know, it's like 1 square root n over log n. That's really abhorrent. So there is a question if there is, there is a question. People ask if there's something better we can do than KKL, and indeed we can. And there is another strengthening of Poincaré's inequality, which was found by Talagrand, which I'll now show. So this one uses a concept called the sensitivity. So sensitivity is a concept which is similar to the influence, but not quite. So the sensitivity of a function, which we denote by h, so it's evaluated at some point x, it's the number of indices, number of edges going out from x, which change f's value. Okay, so how many neighbors you have that are different from you. So for example, in this case, I have this white vertex over here, and I have 3 black neighbors and 1 white neighbor, sorry. So the sensitivity at this point would be 3. Okay, and I did lots of animations for you to follow. So if I go over all vertices and I look at which edges are counted by their sensitivity, then eventually I once again go over all the edges which connect to vertices. So the expected value of the sensitivity is equal to the total influence. And in this case, that means that we can write the Poincaré inequality as a variance. It's smaller not just than the total influence, but actually, okay, the expected sensitivity. So Talagrand, Michel Talagrand in 1994, sorry, maybe I went too fast. Okay. So Michel Talagrand in 1994, he took this inequality and made it slightly better. Instead of having the variance smaller than the expected sensitivity, it's smaller than the expected square root of the sensitivity. Now the sensitivity is always a number between 1 and n, okay, an integer. So taking the square root always makes it smaller. So this is indeed a strengthening of Poincaré's inequality. And this is, this square root of the sensitivity is a sort of weird surface area. I don't actually have any good intuition for it, but nevertheless, it's true. And we see that for the, okay, you can do the calculations, and for the tribes function, the expected square root of the sensitivity is about square root log n, and Talagrand's inequality is not tight. Don't try to do it in your head, it takes a couple of minutes, or at least a couple of minutes for me. And Talagrand's inequality is not tight, once again, okay, because the variance is 1, but now on the right-hand side, I get something which is all of square root log n. But for majority, the expected sensitivity is about of size 1, okay? In fact, if you think about it, for majority, most of the inputs won't change the value at all. There's only like these bordering cases which change the value, and this highly concentrated sensitivity means that the square root will be small. So this is about a constant. You can calculate out this constant if you want. So for here, Talagrand's inequality is tight, and again, by tight, I mean tight up to a multiplicative constant. Okay, so this brings us to our famous diamond of inequalities. I should call it a pearl because it's pearl. Okay, a diamond of inequalities. We have Poincaré's inequality here on top, and we see that on one hand, we have one strengthening, which is called the KKL, which is tight for tribes, but it's really horrible for majority. And on the other hand, we have a totally different direction to go in, which is Talagrand's inequality, which is tight for majority, and it's really horrible for tribes. And of course, there are lots of functions, and I'm not going to go over all the infinity type of, infinite number of functions and compare between them. We have to wonder if they are both maybe part of the same inequality, or maybe there is some stronger inequality which implies both of these. Or maybe we just want to know the actual relationship between the influences or sensitivity or whatnot, whatever relation there is between the edges and the vertices or the variance of the function. Okay, and that's this, these question marks over here. So we in our seminar are not the first people to ask this question. Talagrand asked it himself, and he conjectured the following. Okay, take a deep breath. He proposed this strengthening. So not only is the variance smaller than the expected square root of the sensitivity, but the variance times this beast. Okay, the square root of the log of 1 over the sum of the influences squared. Okay. The sum of influences squared is a term that appears many places in Boolean function analysis. It basically tells you how noise sensitive a function is. So if you if you randomly perturb all the input bits, you want to see what is the likelihood of changing the value, then this quantity right here is a very good indicator of that, if it's really small. So it shouldn't be surprising that, it comes here, everything these inequalities, they're all about the relation between the surface area and the edges. So basically you can see how noise sensitivity comes into play. You want to ask, if I make small changes to the input, which are clustered together, maybe I'll change the value or not. So you can see why these come in, but for the square root and the log and all of this, maybe a different explanation is in order. So Talagrand conjectured this, and it's quite obviously a strengthening of his own inequality. It's not quite obviously a strengthening of the KKL, but as we will soon see, it is, or it will be in a slightly stronger version of this conjecture. And now, we're already almost halfway through the talk, so maybe I should actually state some result. So this is our first and main result of the paper that we wrote, Ronen and I. So this is actually a theorem, not just a conjecture. It is indeed true that the variance times this horrible log is smaller than the expectation of the square root of the sensitivity. So I think it's actually quite nice, okay? Not just because this is a complicated expression, but because we do indeed have some inequality which is tight in both of the nice cases that we saw, which implies both of these inequalities. So what is the actual thing that we proved? Wait, there is a question. Does anyone want there is a variant of KKL. Okay, Raphael asks, there is a variant of KKL due to Talagrand, which makes sense for non-Boolean functions. Is there also a conjecture which makes sense for non-Boolean functions? I don't know, and this is a good question, and I should have to think about it. There is a variant of KKL that applies for non-Boolean functions, and actually there is even a strengthening of KKL, which is accessible to non-Boolean functions, and we'll talk about that in a bit. So I'll have to think about the other question though. Okay, so here's our theorem statement, okay, as you will find it in the paper, more or less. Maybe with, in the paper they don't let us print colors. That's too bad. So we say the following: there exists some function which we call g of f, which is okay, it's a function on the Boolean hypercube, but it's to 0, 1. Okay, it's a real interval 0, 1, and it has the following properties. Okay, so the expectation of this function squared is bounded by some constant of times the variance of f. Okay, so we know that it can't be too large if the variance of f is large, it's small. And so we have this function so that for all p greater than half and smaller than 1, this inequality holds. So we have the variance, we again have the log of 1 over a divided by all of this, but now we have it to the power p and not just to the power half. And this is smaller than the expected value of the sensitivity to the power p times gf. So why is it stronger? Okay, it's stronger in 2 terms. First of all, we have this p and not only half, okay, trivial. But second, on the right-hand side, we now always multiply the sensitivity by some function which is between 0 and 1. So the right-hand side is even smaller, and that's good for us. So of course, this version, and this version is what we prove using our stochastic method. And of course, this version is, it implies Talagrand's inequality. And let's do just some quick calculations to show why it implies KKL. And maybe then we can go the other way around. So we start with this inequality. Okay, this is what we proved. Let's take the right-hand side and apply the Cauchy-Schwarz inequality. I see a question, I will answer it in a minute. Let's take the Cauchy-Schwarz inequality here. So this as expectation of the product is smaller than the product of the square root of the expectations. And now we know that the expected sensitivity is actually equal to the total influence. We saw that like way back 5 slides before.
Renan, a question. Was it square root of HF in the bound?
Yes, there should be a square root here, sorry. But then it will work out, right? Because we take a square here inside. Good catch. You have 2 points.
Yes, thanks.
Good. I always, I usually buy lunch to the one who has the most points at the end of the lecture, but now we're all at home, so no lunch. Yeah, so
you can order takeaway for me.
To all you Tel Aviv people, takeaway from Rehovot, do you want it? So yeah, so now this holds, and this the expected sensitivity is the total influence, as we saw before, and our theorem stated that the expected value of t squared is bounded by some constant times the variance of f. Okay, so we have this, and if we plug it in, we get this inequality. Now we can take the square of both sides, okay? So the variance squared times the log is smaller than this fellow over here, the variance of f times the total influence. We, do whatever we have to do, rearrange stuff, and eventually we get this inequality. So the variance of f is smaller than a constant times the total influence divided by the log of this guy. So this is already looks like KKL, okay? Only we have the log of, you know, this denominator 2 plus e over the sum of influences squared, rather than just the maximum influence, okay? So that's the difference here. But if you actually, I'm just rushing up for calculations here. If you like do a case-by-case analysis of what is the maximum influence and how this sum here behaves, then you just get back KKL. We're gonna skip over that a bit. So this was just to say that indeed this inequality implies both Talagrand's inequality and the KKL, so it's strong. So now we have a question from Slamak. Did you construct G explicitly? And the answer is yes. I mean, it's not just an existent result. You can basically follow it, but the construction is stochastic in nature and has lots of expectations of this weird stochastic process. So like if you actually want to calculate it by hand, I don't think you will be able to, but maybe to simulate like numerically on the computer, you will certainly be able to do it. Renan, try disabling the video. Okay, okay. How do I do this? Stop video. Maybe it will be better. Okay, is everyone happy up to now? Up to a constant? Okay, great. Okay, thank you, Larson. So now someone mentioned KKL inequality, and I want to mention another inequality before we move on to proofs or proof ideas. Okay, I know I talk a bit quickly, and this Zoom is like shaky online connection, so we won't go too deeply into the proofs. But I promise that you will see some very pretty pictures, which I put a lot of hours into. So, you know, at least will be satisfying in this sense. But before we do that, let's talk about another Talagrand inequality. And, you know, Talagrand likes to extend inequalities. So here it is. It's another extension of KKL, a strengthening of KKL, which says the following. Okay, the variance of f is smaller than a constant times not just the total influence divided by the maximum influence as we had before, but now it's 1 plus the log of this individual particular influence. Okay, so we don't go over the maximum influence, we have this individual particular influence in this sum. Ron said, at least for me, the chunkiness was pretty much fixed. Okay, okay, I see you want to see my handsome visage, so I will turn back the video. Okay, let's turn it back on. So this is another inequality by Talagrand, which is another generalization of the KKL inequality. And you know, before we talked about the edge boundary of a function, right? The number of edges connecting black and white vertices. And now we can also talk about the vertex boundary. And this inequality and the vertex boundary are quite connected. So what is the vertex boundary? So the positive vertex boundary, or the inner vertex boundary, if you want, it's all the points on the hypercube such that f of x is 1, and there is some neighbor of x which is -1. Okay, so f changes value. And here, if I have some, you know, function, I now colored in blue all the inner vertex boundary. Okay, all the points which are 1, which have some neighbor, which is -1. So this point, white point here, for example, is not in the inner vertex boundary. And the outer vertex boundary is defined similarly. It's all the points in the hypercube for which f gets a value -1 and has a changing neighbor. So, you know, this can differ from the edge boundary by a factor of up to n, right? Because there are n times as many edges as there are vertices. And the theorem that we proved related to this inequality, again using stochastic methods, is the following. If the variance of f is greater than some other constant times this sum on the right-hand side, okay, so this relates to one Ron asked before about tightness up to a constant. So we know it always has to be smaller, okay? Talagrand, you know, says this. And now we say if this value is greater than some other, probably much smaller constant than this one, then something happens. And what happens is that the amount of vertices in the inner vertex boundary and also in the outer vertex boundary is at least greater than the variance of f. Okay, and this is very nice. Okay, it's always good to keep in mind the cases where the variance is a constant. Okay, variance going to 0, it's like very degenerate functions. If you think about functions like what we talked about, tribes, dictator, parity, majority, all of these have constant variance. So if you think about this variance as a constant, then it says that if you have some balanced function, okay, constant variance, which somehow satisfies this inequality, then there are many vertices in its vertex boundary. And this is both, I wrote here the inner vertex boundary, but it's also true for the outer vertex boundary. And while proving this, we also proved the original Talagrand's inequality over here. Okay, so these are basically our two main results. Okay, we have this, we like to call it a stability result for Talagrand's inequality, which says something about if you're almost tight in saturating the inequality, what can you say about the function? Well, we can say something about the vertex boundary, and okay, this is going really slowly. And we also have Talagrand's inequality, which we proved here. So are there any questions on these two inequalities, or what they mean, or what they do, or about life in general? Okay.
Renan, I have a question. You mentioned several functions which have which are balanced, meaning the variance is 1.
Yes.
Also in mind an example of a function which is not balanced, where you get an interesting bound on the variance from these inequalities?
Do I have a function which is not balanced, which I get an interesting bound?
Because if it's balanced, the variance is 1. You don't need the inequalities to know the variance.
What do you mean you don't need the inequalities? I mean, this can be, this sum on the right-hand side can be greater than 1, or you know, it can be a constant, or it can go to infinity.
The variance of the Boolean function is at most 1 in any case.
Right, right.
And 1 if it's balanced.
Yes.
So I was thinking more of the upper bounds on the variance when they are useful.
Sorry, I did not.
Okay, never mind. It's not important.
One, just usually those things are useful to give a lower bound on the right-hand side rather than an upper bound on the variance. It's usually the case that you know what the variance is, but it's useful to get a lower bound on the sum of influences or something like that.
Ah, I see. All right. This is a different point of view. Thank you.
Like Ronen would want to say that maybe if you can show this sort of thing, that you can show noise sensitivity and stuff like this.
I see. I see. Very good.
Okay. Good. So just a couple of words on how these inequalities are usually proved, like, you know, KKL and Talagrand type inequalities. I usually proved using a heat operator and hypercontractivity. Okay, lovely words from analysis. So ultimately, it's all about noise sensitivity and how these functions behave when you make small perturbations to their inputs. So we can define the heat operator, which we call T rho, to be the following. So T rho of f, how is it evaluated at point x? We just take the expectation of f of y, where y is correlated with x. So with probability 1 over rho divided by 2, it's just the same bit, there's no change. And with probability 1 minus rho, we flip a bit. So if we think of rho as close to 1, okay, so the y is highly correlated with x, then with high probability, it just stays the same, and with low probability, we just flip a bit. So this is what the noise operator does. And we can think of y as an uncertain version of x. Okay, so having chosen x, then y is distributed over all the hypercube. Here is another image we have. Okay, so x is this lower point over here, and y is given probability. Okay, y can take value generally in any point in the cube, but it has really low probability of being far away from x, as you can see by the dark color of far away vertices. But it has high probability of being close to x, as you can see by the light color. And if, for example, as in this case, x is I don't know, some vector, okay, 1, 1, minus 1, then the expected value of y is rho, rho, minus rho, and rho. So we can think of y as a hesitant version of x, okay? Or if we can think of it as a hesitant version of x, where it's sort of decided that its bits want to be like x, but not quite, okay? There is still a small probability of differing from x. Let's think of it like this. And in this sense, the heat operator is called the backward operator sometimes, because you start at some x and then you make a noise. And so you start at a definite point x and then you somehow distribute across this entire hypercube. And then there's a famous inequality called the hypercontractive inequality, which is that this heat operator is a contraction. Okay, so the 2 norm of the heat operator is always smaller than the 1 over rho squared norm. And normally would have it the other way around for Boolean functions. So this is a very useful tool. It was useful throughout all of the last century and still useful today. And then the proofs usually go via Fourier analysis. So every Boolean function can be written, can be decomposed in Fourier monomials or Fourier characters. So it's just the sum of coefficients times monomials. Okay, it is products of individual bits. And then the variance, it's a fact from Boolean analysis. The variance is just the sum of these coefficients squared. But you also know what happens to these coefficients when you apply the noise operator. And then you can actually compare, this original variance to how the noise affects it by use of the hypercontractive inequality. And eventually, okay, after like 10 lines of calculations, you can get a inequality. After 20 lines, you can get Talagrand's inequality and stuff like this. This is basically on one leg. This is how you normally do it. And our approach is, it's similar in the sense that we do use noise, okay, and we use these versions of the inputs, but we go from a totally different direction. And let me tell you what I mean. So just a word on this expectation and the noise. Okay, I'm getting a word from Zoom that my connection is unstable. Do you hear me? Yes?
There was a momentary gap, but now it's okay.
Okay, like life. So everything in life is expectation, and this is true for Boolean functions as well. So, who were our main characters in our inequalities? It was this expected value of the sensitivity, the variance, which can also be written as an expectation, and the total influence, which is also an expectation, the expectation of the size of the gradient squared, the norm of the gradient squared. And what we like to do is we like to generate the uniform random variable piece by piece instead of all at once. And this can give us some information on the process or on the function or on how it behaves. These sort of martingale methods or information revealing methods. So instead of just doing, generating the input all at once, we generate it bit by bit, for example. It's just an example, not exactly what we do. So we start with the vector where we don't know the inputs at all. And then we start let's say the expected value of the function. And as we reveal a bit, we learn something new about the expected value of the function. And we also just see this very lovely animation. So this is the idea behind our proofs, only we don't exactly reveal the information bit by bit. Rather, all the bits, we reveal all the bits infinitesimally and simultaneously. Let me say what I mean. So basically what we have is we have a martingale, okay? And here is finally the analysis, okay? Everyone with the camera turned off will suddenly, oh, look, finally analysis. All the continuous stuff that we know and love. So we have this, we define a martingale, BT, which has n components. It's a stochastic process, and we will define it to have the following properties. Okay, so every entry is IID, okay, easy to do. At time t, the absolute value of BIT is t, okay? So if I draw this stochastic process, I know that it has to be always on, exactly on these two lines. And it's a martingale. Okay, so that's all I demand it to be. And just a reminder, so a martingale means that the expected value of this process at time t, given the history, okay, given everything that happened up to time s, it's exactly equal to the process at time s. So this means now, martingales love to jump around. Okay, so if I think about this process as, let's say it's already on the positive, so I know it's somewhere around here where my mouse is, then as time progresses, it should, move up. Okay, it wants to stay with absolute value t, but it also has to stay a martingale. So sometimes it just has to jump down in order to keep this expectation constant. And when you do the calculations, this is the sort of process how it looks like. Okay, so all of these processes start at 0, right? B of 0 is always 0. And then at time 1, they're always either +1 or -1. They're independent. So at time 1, this entire vector BT is just uniformly distributed in the hypercube. But in some sense, we are building the randomness from the bottom up. Okay, unlike the heat operator, which started already at some point x and then went backwards, and, put some randomness to give us some diffuse distribution on the hypercube. Here we start at the exact center of the hypercube at the point 0, which is in the center of the -1 continuous -1,1 hypercube, and then we build the randomness, build it up. And if the value, let's look at this green function right here. If I'm already here at this point, then I know that with high probability, I'm going to continue being positive and eventually reach +1. Of course, it's not always the case. Maybe like in this blue one, I'm probably going to be negative, but oops, I jumped up. So this is like a sort of uncertain process, which eventually at time one gives us a uniform random vector. And okay, I just made a nice drawing to see how it looks like in 3 dimensions. So each one of these, each color here is one 3-dimensional process, and you can see how it goes to other different corners of the hypercube. Okay. So one important thing here is that this is a martingale. We can calculate the jump probability. So let's denote by P the probability that it changes sign in some small time frame epsilon. Okay, so the probability that at time t plus epsilon, the sign is different from time t, given that we know what happens at time t, for example. So it's a martingale. So I know that the expected value of my process at time t plus epsilon is just the value of the process at time t. This should be, this S here should be t, sorry. It's just t. And with probability p, I change the sign. So I have here minus t plus epsilon. And it's probability 1 minus p, I don't change the sign. So it's t plus epsilon. But on the other hand, I know that at time t, bt is just equal to t times the sign of bt. Okay, because it's always, the absolute value is always t. So then I do lots of animations, and I eventually get this result over here. That the probability to jump is proportional to epsilon divided by, it should be, epsilon divided by 2 times t plus epsilon. And as I take epsilon to 0, I can think of what is the instantaneous rate of jumps, right? I can think of this as a process which at every moment in time has to decide whether or not it jumps or not. And the probability of it doing so, or the density of this doing so, is 1 over 2t. Okay, it's basically a Poisson jump process, only it doesn't stay constant. In the middle, it goes either up or down. Okay, so just a reminder, what is a jump process? A Poisson process has rate lambda. If I look at the difference between 2 values in time, if this difference distributes like a Poisson random variable, where the rate is equal to the integral of the rate function, or the Poisson, the probability of jumps. And different intervals are independent. Okay, usually it looks like this. So our process is actually really reminiscent of a process like this, a Poisson process, only with 2 changes. First of all, it's not constant between every jump. It either goes up or down, depending on whether it's positive or negative. And second, the rate is a function of time. Okay, it's 1 over t. And you might get worried that it has infinitely many jumps near 0, and it does, but I mean, that's fine. Okay, the process can jump infinitely many times if it wants to near 0. No problem there. And the thing that's important for us for Poisson processes or jump processes in general, which have jumps but are otherwise smooth in between, is their quadratic variation. So the formal definition of a quadratic variation is we take a partition, okay, we partition this interval, and then we look at the sum and the differences, the square of the differences at these intervals, and take the partition size to 0. Now for the Poisson process, everything here is flat. So we'll only get actual any contribution when there is a jump. Otherwise, this partition, if we take 2 different values here in the same flat region, same plateau, nothing will happen. But we just get a sum of squares, basically. So for jump processes, the quadratic variation is equal to the sum of squares of the jumps. And this is true also, not if we have this standard Poisson process, but also if this function in between is any smooth function, as in our. Okay, and you can probably already see where this is going, right? Martingale is the quadratic variation expectations, like all of the pieces start to fit together to see the things we can do. So let's build it up. Okay, let's see what we can do with the process that I laboriously defined and how it actually relates to all these inequalities which we talked about before. And then I hopefully didn't give you too much of a headache with this. Okay, should we do, no, let's skip this. Okay, so how to use. So as I mentioned before, every function can be written as a sum of Fourier monomials. Okay, it is called the Fourier decomposition. It's a unique decomposition. You can show it either by brute force, just apply your standard orthogonal projections and everything. So we have this Fourier coefficient and the product of individual indices, and we go over all subsets. So how to use our function? Okay, I mean, this is a Boolean function, but because we have this polynomial representation, we can just plug in our process bt. So now we have some, and this gets fractional values. So now we effectively extended, or actually we took the harmonic extension of the function to the hypercube. So now we can look at ft which is the value of the function f of bt as a function of time. Okay, this is going to be some continuous thing. Only what do we know? We know that at time 1, bt is uniform with the hypercube. So time 1, the function is just going to get either +1 or -1. Okay, let's see some nice images. This is basically how it looks. I think this is a simulation of the majority function on 15 bits or something like this. So we don't know what the underlying process bt is. Okay, there are all sorts of jumps in all sorts of coordinates at different times. Sometimes a jump may change the value of the function, sometimes it may not. And we see what happens here. So these are really convoluted functions. They are martingales, by the way, because each one of these individual terms, because the bits are independent, is a martingale. So we have a sum of martingales, which is still a martingale. And we can think again, using our noise analysis, that as time goes on, the function's value starts at random. Okay, it starts at the expected value of the function, actually. And as time goes on, it sets which value it's actually going to get, okay? It decides upon which value it's actually going to get. Okay, lots of things like this. And again, this is a jump process. So we know that the quadratic variation is equal to the sums of squares of jumps. And what is a jump at some time t? So why do we jump in the first place? We jump because the underlying process bt jumped. So there has to be some coordinate which jumped. So let's say that we jumped in coordinate I, so bt flipped, and this means that in this expression right here on the top of the slide, one particular coordinate flipped its value. And so what is the size of the jump? It's just a derivative, which is exactly what happens when you flip a bit, if you remember from way back. So basically, and by how much did we flip? By 2t, because we go from +t to -t, or from -t to +t. So the jump is of size 2t. So this jump size is 2t times the partial derivative in direction I of f of bt. Okay? Yes, good. So now we can again talk about the quadratic variation, which we know for a martingale like us. It's just a sum of, it's both the sum of squares of jumps and also the expected value of the quadratic variation is equal to the variance of the martingale at time t. And now we can put everything together. Okay. So on one hand, the variance is just equal to, okay, the variance of f as a Boolean function, right? When we have uniform distributed input, this is just equal to the variance of f applied at p of time 1, because that's uniform. But I know from this equation here that the variance of f at b of time 1 is just equal to the expected quadratic variation, which is the sums of squares of jumps. So now we have this really ungodly expression right here, right? How do I know what these sums of squares of jumps are going to be? But fortunately, if you recall from earlier, I mean, I just didn't tell you about this rate, the jump rate for nothing. We can actually take this expectation over where the jumps are going to be. And by changing the order of summation, we can say, okay, the probability at every point in time to jump is 1 over 2t. So let's exchange the order of summation. We'll get an integral instead, but that's okay. Okay, there are some details you need to do. But eventually you get this equality. Maybe it's outlined even. Okay, so the variance of f is equal to the expected value of, we go over all coordinates that can jump, and we take an integral over t times the size of the jump squared, or in this case, the derivative squared. And now we are partially happy. Okay, this is like only half the analysis. I will be finished in 5 minutes, don't worry. But now we're already in a good place, and we see how all the pieces fit together more or less. Because we know what is expected size of the derivative, right? So it's basically the influence. Every time before, when we talked about Boolean functions, the expected derivative squared was the ith influence. So we can see how these play a part. And now that we have this integral equation, we can apply real analysis stochastic techniques. Like we can say, okay, maybe this thing inside is bounded by maybe a differential equation or by some other equation. And then we can say, we can put a bound on how large this integral can be, which in turn puts a bound on this variance, which is exactly what KKL and Talagrand and most of Talagrand's inequalities are. So this is basically what's going to happen, only with some extra punch, okay? Because maybe bounding this process, the expectation of this process is hard, so we have to look at individual paths. That's eventually what we do. But as as one reviewer commented on our paper when we submitted it, we can already prove the KKL inequality from this inequality alone. Okay, this is all you need. Like if you guys take this inequality home and then try to analyze the right-hand side, you'll be able to eventually prove the KKL inequality. But this is a very bad way of doing it. I mean, a very difficult way of doing it. So the strength of the method of all these stochastic processes and martingales is not just in this integral alone, but rather in the fact that now that we have these individual paths, we can follow them around and see how they behave. So I'll just give a small outline about how we do this. And then I guess if people want to stay afterwards, we can talk or read the paper or send emails or whatever. So again, this can prove KKL and can basically also prove Talagrand's inequality. But if you want, the two stronger results that we showed, then you have to go a bit further. So what do? We talk about stopping times, or we ask how large individual paths can be at particular times. Let me just put a slide. So this is what we want to prove. This conjecture right here. Okay, the expected square root of sensitivity is larger than this horrible right-hand side. So what is the expected square root of sensitivity? Well, the derivative in direction I is 1 only if there is some change. So the sensitivity is just equal to the sum of the squares of the derivatives, or basically the norm of the gradient, square of the norm of the gradient, right? It's just the square of the norm of the gradient. And if we take the square root, we just get the expected average sensitivity square rooted is the expected norm of f, of the gradient of f, sorry. Okay, and again, we can use our martingale process. This means that the expected value of the gradient of f at b at time 1, where b is this horrible jumping process. And so we can now define a continuous version of this process. Okay, we have psi of t, we call it psi of t, and it's equal to the norm of the gradient of f at time bt. Is this a martingale question? You can unmute yourself, Ron, if you want to say it.
I don't think it's a martingale. The norm looks like something very problematic for the martingale. Maybe sub-martingale.
Right, it's not a martingale, but it is a sub-martingale. Excellent, another 2 points. So this is a sub-martingale, okay, because inside, what's inside is a martingale, well, without the squares, whatever. But now that we take the norm, it's a sub-martingale, so we know the expectation always smaller. So what do we have to do in our case? We want to show that the expected value of psi time 1 is larger than this expression on the right-hand side. And we will use the fact that psi of t is a martingale. So martingale means that if we stop it and at any time smaller than 1, then we know that the expected value of psi 1 is smaller than the expected value of psi at the stopped time. So what we're going to do is we're going to ask, is psi of t large? And by large, I mean larger than this right-hand side, or something that's proportional to this right-hand side, for some t smaller than 1. That's all we have to do. And if we look at psi, okay, we denote some threshold level alpha. And sometimes this process psi may go down, or sometimes it may go up and may cross up over alpha. So we're going to ask, is it larger than some value alpha at some point in time, which is smaller than 1? Or more formally, we define a stopping time, tau alpha, which is the smallest time such that psi t is larger than alpha. And if that doesn't happen, it's defaulted to 1. And so by the submartingale property, the expected value of psi at time 1 is larger than the expected value of psi at time alpha, which is always larger than alpha times the probability that tau alpha is smaller than 1, right? Because if indeed tau alpha was smaller than 1, then we stopped because psi was larger than alpha, so we get this. And eventually what we'll basically show, or what we basically do, is we set alpha, this green alpha here, to this square root over here, and then we set this probability, we show that it's proportional to the variance eventually. And how do you do this? Use what is called level inequalities, or in our case, it's called the level 2 inequality. This is, okay, it can be shown using various methods. It gives you a differential equation on the size of the derivatives, okay? So here we have the magnitude of the gradient of f, and it's bounded by some constant times the magnitude of gradient of f itself. So this says that as long as, as long as the gradient is small, the change in f also cannot be small. But eventually, I mean, this gradient is going to have to be large, if we have some inferences. So this means that all of the change of the function psi happens near the end of the function. So it's going to be small all the time, small, 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 and then it's going to jump up. And the place where it's going to jump up is about of size. It can be shown, okay? It's not trivial, you have to prove this, but it's about the size of the log of this horrible thing that we wanted to prove back there. So it's going to be small, 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 and then suddenly explode up to have a very large value. And when it does this, we can show that the quadratic variation itself is also large, okay? And I did not cheat here, okay? These are actual simulations which show that about the time when, you know, psi crosses alpha, then the quadratic variation gets a very large jump. I was very happy when this happened in the simulation. And more formally, or more technically, if you want, we're going to set alpha to be whatever. You know,
Renan, just note the time, please.
Yeah, it's the last slide. We're just going to show two things. So first of all, the quadratic variation at times when psi was not large is very small. Okay, it's proportional to epsilon, very small, tiny. And second, that the quadratic variation has to be large in general. And okay, I won't elaborate more on these methods. You can do it, but combination of both of these together mean that when you do finally jump, you have to jump a great lot, which means that psi is going to be large. Okay, this is the final slide, the actual final slide. So I guess I've said what I wanted to say, and maybe you heard what you wanted to hear, and maybe not. So you are free to ask questions.
Okay. Thank you very much, Renan, for an excellent talk. Thank you very much. Please, anybody wishes to ask
Yes,
a question?
I have a remark, some information about the martingale tools you use. Are you aware of the literature of from 77 to the early 80s, David Gilad, Barlow, Proter, Mark Yor? David Gilad in 77 proved that every positive sub-martingale is the absolute value of a martingale. And he proved it in distribution, but Barlow in 82, I think, proved it almost surely by doing the method you apply. That means by taking the positive sub-martingale and its minus and building a Poisson process that switches from one to the other, and this is the way the martingale is produced. That's so worthwhile to look at the...
So I did not know this, and I'll be happy if you post a link in the chat or to my mail or whatever, because I do not know these constructions.
Okay, I will.
Yogesh, we don't hear you so well, and try again.
Hello. Yeah, can you hear me now?
Yeah.
Okay. So I was wanting to ask two things. One is, how does this compare with Talagrand's L1, L2 inequality? I think you showed a second inequality of Talagrand. Probably, I do not know if that, I think, is some form of L1, L2, I guess.
Let's see. Like you want?
Yeah, the second inequality is exactly the L1, L2 inequality.
Yeah.
Just the Boolean version of it.
Okay.
You're probably
so
talking about the one in.
Yeah, I'll comment about this. So we even had a comment right in the chat before, which talked about non-Boolean versions of these KKL-like inequalities. So this is a stronger version, right? This inequality right here is stronger than KKL, so that's good. And if you replace this influence on the numerator by, I think, the L2 of the derivative, and here in the log, this ratio by L1 over L2 of the derivatives, then you get another, continuous variable version. But there are actually other ways to extend this, I think, and there's been a lot of literature about this.
Okay.
Yeah, you had two questions, right?
No, I was trying to understand. So this is also implied by your inequality.
No, it's not implied directly by our inequality, but we also prove it using the same stochastic method.
Same stochastic. Okay, fine. Yeah.
I have a question. Okay. Perhaps it's not the best use of your time, but does your approach, can you prove this way the hypercontractive inequality, the classical one? It seems just right there, because you can increase the noise from 0 to rho, And hopefully the hypercontractive inequality, which is always just proving it is just like some weird calculus exercise and tendering. Do you have a martingale proof for that?
I can't say right now. Ronen was going to say yes immediately.
Yeah,
but,
yeah. It
I mean,
gives a proof of the hypercontractivity.
But you have to work a slightly bit right now.
Okay. I mean, it's using related ideas of just writing a PDE for that relates between the quadratic variation and the derivative of the quadratic variation. You can like write something that gives you hypercontractivity.
So that would be just really nice to see how, I guess you're just applying Dub's L2 inequality and you somehow get, or some LP, you know, the, I don't know.
You don't, no, you don't need any it's actually to get hypercontractivity, you don't actually need to say anything about like, you can only do it everything in expectation. So you can just look at the expectation of the martingale and the expectation of the square of the martingale at different times and do calculations on this. So you don't need any more advanced technology of like Dub, stopping times, whatever. This you only need for like the improvement of the Talagrand thing.
Okay, wow, that's terrific.
Do you think it's going to make the hypercontractive inequality more lucid in any way? Well, maybe.
Yes.
Maybe I have a question. So sometimes these inequalities are also used to get upper bounds on variances, not just lower bounding the right-hand side. For instance, I think for first passage percolation, people were using it to get a sublinear bound on the variance of the passage time. So n over log n bound started with Itai's work and so Itai Oded and Gil, was it? I wonder, your methods then improve upon this because you have a sharper, in some sense, sharper inequalities because you can also establish this. Do you believe for applications like passage percolation, you can get sharper upper bounds?
So I think Ronen is working on this as we speak, right?
So basically, I mean, it has the potential to do it. So yeah, I mean, the same thing works for, as you said, the Binyamini, Kalei, and Shram results. Basically uses the Talagrand thing, only just a slightly more general version of it. So for the Talagrand thing, you don't really need the function to be Boolean. You only need the increments to be integers. That's really enough. So that works for first passage percolation. And basically our technique can tell you something like, if the BKS bound is sharp, then we can characterize what, well, I guess it's going to be hard for me to formulate it correctly, but then we can deduce that the first passage percolation has a very, very specific structure that you only need to somehow refute that it has this structure. This will give you an improvement over BKS. So, you know, if you want, I can offline, I can tell you exactly what this thing implies.
Okay, sounds interesting. Thanks. Other questions, please?
Yes, I have one other question, a little crazy maybe. It's relating to something completely outside, but somehow this reminds me that the setup is similar to coalition games in game theory, where the corners of the hypercube are coalitions. The value of the function f, whether Boolean or more general, is the payoff of the coalition. And the influence functions, the derivatives you use are the marginal contributions of players. And I think that even the influence function that you build is maybe completely the same or similar to the Shapley value in games. I wonder if there is anything of interest by looking at it from the point of view of games. I don't know. But I would I would suggest to look into it. The Shapley value of coalition games.
Yeah. I don't know, but there's definitely some connection. I know that when I looked up the references for these type of things, and I think the first isoperimetric inequality on the hypercube comes from a game theory paper, right?
Uh-huh.
So
Okay.
there's bound to be something, but I can't tell you about these particular inequalities. But again, it's a good thing to look into. Do you want to do it?
Huh?
Do you want to look into it? I ask.
Well, I might. Okay, I'll think about it and I'll try to read. So
I will also look, of course.
So okay, I'll ask you about getting at least the presentation and connect with that. I'll write you about it.
Sure.
The presentation is available on the website of the Horowitz seminar.
Yeah, good.
Any other questions or comments? Okay, if no other, then let me say that next week we'll have Isabella Stuhl from the University of Pennsylvania. I'm considering making the seminar next week, start a half an hour later, but I'm not sure if I will, so stay tuned to the announcements, please.
Okay.
So let me stop the recording now, but we can still stay and talk to Renan.